Physics Bites.
Physics Bites.
A science podcast in English by the students of Notre Dame d'Instruction.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre Dame d'Instruction here in Paris. We are with two new senior students here who are going to talk to us about chaos theory and theory of complexity. It's a very interesting topic. We hadn't treated that before at all. So I'm going to let themselves introduce themselves and we'll get the show on the road.
So hi everyone. So my name is Carla and
this is your third year doing Daniel with us?
My third year. And so this time I'm going to talk about chaos theory.
Right. Now you're also doing physics major with me, and you're hoping next year to get into physics and sciences with the hopes of becoming a physicist at the end. Is that right?
Yes, exactly.
Okay. And our second expert?
Hello, my name is Jane, and it's also my third year in Daniel class.
Right. You've been a student of mine in Daniel for the last 3 years, but you stopped doing physics as a major after grade 10, right?
Yes.
Right. But that hasn't stopped you from doing Daniel and doing a pretty physicsy topic of chaos theory. So let's get started. Why don't we begin with a sort of brief summary of what you guys talked about? We'll go point by point, and then we'll get into the questions as you bring up the different parts. Okay? Who wants to start?
Okay.
Okay, Carla,
maybe
you
I
can start.
Because
Sure.
I'm going to talk about about what is really chaos theory and about the butterfly effect, which really has a link with chaos theory.
Right, and which is the one part of chaos theory which everybody in popular culture knows about.
Yes.
Okay.
So today, modern measurement tools, they are often imprecise, but in most physical systems, small errors or small changes in the initial conditions, they don't really have an impact on the evolution of the system. So for example, if we have two identical pendulums and we release them at slightly different angles, we notice that they behave almost identically. However, there are some systems like double pendulums that are highly sensitive to initial conditions, meaning that even tiny changes can lead to really different outcomes in the system. So this sensitivity to initial conditions is a characteristic of chaotic systems. So this chaos was discovered by Edward Lorenz, who was a meteorologist, and he realized that when trying to do a model of the weather, he found out that really small differences in input values due to the rounding from 6 to 3 decimal places led to dramatically different weather predictions.
Right, just so we can get a historical context on this, what year, about what a period of time was this happening?
I'm not sure about the exact year, but I think it was in the 1960s.
Right, and this is one of the reasons because why this was the case was I think this is one of the first times when we were starting to use like very basic computers for modeling and chaos theory and chaos, or at least modeling of dynamic and nonlinear systems is very computational, which is why it's something that came about kind of in parallel with the invention of computers and the commercialization of computers. Go on.
Yes, and so also this was a very simplified system because it had only a few variables, but it was very chaotic. So so in essence, so weather patterns, they may appear repetitive, but they are never exactly the same.
Right.
And so they make long-term predictions impossible due to the kind of exponential growth of small measurements error.
Right.
So to visualize chaotic systems, scientists use something called a phase space. So a phase space is a three-dimensional space where each dimension represents a variable. So in Lorentz model, the system state traces a path because the system is represented by a point which has 3 coordinates, so one for each variables if we have 3 variables, but it can be more. And so the system's state creates a path as it evolves, which forms a kind of butterfly-shaped structure that we call the Lorentz attractor.
Right, just so we're clear, the path that you're talking about is not like a physical path, it's what we call a phase space. And the phase space, do you know what the description of a phase space would be?
So a phase space is a three-dimensional space that represents the evolution of a system.
Right, and so it's the way different parameters evolve in terms of other parameters.
Yes, because
why is it three-dimensional in this case? Do you know?
Because we have three variables, but
right.
I think it can also be. If you have only two parameters, then it can be two-dimension.
Right. So it has as many dimensions as there are parameters in our model. So the more complex a model is, the more higher dimensional the phase space would be.
Yeah, but it's harder to visualize, I think, if they are more than 3 dimensions.
Of course.
And so we can actually see how chaotic systems behave with this phase space, because if we take two nearby points at the beginning, we notice that they diverge quickly, but they always stay within the structures, which shows how chaos can have a kind of order. Those points, they go through the same part of the attractor at some point, but just not at the same moment, and they never go twice.
So if I can just maybe ask you a question. So if a system wasn't chaotic, if a system was perfectly periodic, what would the path in phase space look like? Do you know?
If it was periodic, then it would look kind of like an orbit, I think, or
like a closed loop. Right. Yeah. It would only be one path. It would be a closed loop, and different points in that phase space would correspond to different points during the movement of the oscillator, where the parameters have, certain pairs of values, but it would be very repetitive. What makes this different is that the loop is never quite the same. So each time it goes around in this phase space, it never comes back to the same place.
Yes, exactly. And also it's interesting because we can try to kind of control chaos by making the system stay on only one orbit, but that's very hard to do. Okay. And so basically this structure is called an attractor. And the definition of an attractor is that it's a state or a set of states toward which a system tends to evolve over time. And so often chaotic systems, they show long-term patterns, so attractors, despite their short-term unpredictability. So for example, if we take the butterfly effect, small disturbance like a butterfly's wing flap, they can change the short-term weather, but they won't change the long-term climate trends. And so historically, chaotic behavior was observed in systems like the three-body gravitational problem, which are highly sensitive to initial conditions, because if we use Newton's law, and it's very easy to describe the gravitational force during two bodies, but if we add another one, then it becomes very complex because all of the body influence each other, and it has a chaotic behavior.
So just let's go into, because I think this idea of sensitivity to initial conditions is one of the most important aspects of chaos theory and modeling of these chaotic systems. Can you just do you have an example you can give of something that is so sensitive to initial conditions, for example? Just so we can better visualize in our mind, I guess, what we mean by a system that's linear and what is non-linear.
So, for example, I think, I talked about examples in the presentation. I don't know if it's, for example,
just anything that's even basic idea of helping somebody who has no idea what we mean by that, sort of better get a feel for it.
So, for example, if we take two double pendulums, so I don't know if you visualize what a double pendulum is.
Just it's like an arm that has an elbow.
Yeah. So you have one simple pendulum, and then and then there's another one attached to the end of the first pendulum. And so if we take two completely two similar pendulum, like the same, and we release them at really at
like a similar
angles,
starting position.
Really similar starting position. Then we notice that the path of the point that is on the outside of the pendulum, it's completely different for the two systems.
Right.
And so, which is a bit weird, because usually we would think that if the difference in initial condition is very small, then that means that the path of the points will be kind of like the same, but it's not. And so this is an example of a chaotic system.
Right. So this is an example of what we would call a non-linear system, because like you just said, if this was linear, so if I make the initial conditions like 2 degrees further to the right, the final condition would also be 2 degrees further to the right. And 2 degrees to the left would be 2 degrees. But this is not the case for a double pendulum because it's not linear. I guess another analogy would be I think we talked about this in class. So if, for example, getting to school from your home was linear, if you leave home 1 minute late, you get to school 1 minute late. If you leave home 5 minutes late, you'd get to school 5 minutes late. But that's not how it is, because if you miss your first bus, for example, you'll get your train late. Maybe the next train will be like 20 minutes later. And then if you miss that train, maybe the third train is like 6 hours later. So 1 or 2 minutes initial conditions that are different would result in the final difference of like maybe 6 hours.
Exactly.
Right? So that's what we mean by nonlinearity. Okay.
And
Go ahead.
And also, like in a system that is ruled by nonlinear equations, it's basically like for one input, I think you can have also different output each time. Whereas for a deterministic system which follows linear equations, then for the same input, it will always be the same output, and there's only one output possible.
And in the case of Edward Lorenz, which you mentioned earlier, what was the difference in initial conditions that made such a huge difference in the behavior?
I think it's because he had his model of the weather, and he used to put the same initial conditions and let the program run a bit. And at some point, he decided to print the last values that he had. And when he came back to his computer, he actually like put those values instead of the usual initial conditions.
But he typed it in by hand, sort of what he had on the
But on the paper that he had printed, I think there were only like 3 decimal numbers, and on the computer's memory there were 6 decimal numbers. So this is a very, very small difference. But this small difference actually made the system completely
like the weather predictions that his system was making.
It was completely different from what he used to see, and so that's how he realized that a small difference in the initial conditions can have a big effect on the results.
Right, and this is what very colloquially we call the butterfly effect. Do you want to maybe tell us what we mean then by the butterfly effect?
Yes, because the butterfly effect, as we usually know it, is that a small event can have a huge impact or like huge consequences. And so, for example, like if a butterfly flies, I don't know, in Japan, then maybe it can prevent a tornado in Florida or cause one.
Right, so this is what we mean by the butterfly, so that the flapping of the wings of the butterfly would correspond to these tiny little changes in the initial conditions, which get amplified through the nonlinearity of the meteorological system, which the result would be some weeks later as a hurricane coming up in some other part of it. Okay. You also talked about there's a link between attractors. There's fractals that showed up in the middle there with chaos theory. Do you want to maybe give us a bit of a detail what you mean by that?
Yes. So actually, attractor is like the set of states towards which a system evolves over time, and there are some attractors that have a fractal structures. So a fractal structure is basically when you look at an attractor, and when you zoom on a part of it, then you find the same structure, and this structure repeats ad infinitum. And so for example, those attractors, we call them strange attractors, and actually the Lorentz attractor is a strange attractor because it has a fractal structure. And it's not really obvious in the first place because you can't really zoom really close to actually see that fractal structure, but it has been mathematically proven, I think in the early 2000s, and so it exists. And there are systems that it's easier to visualize the fractal structures. So for example, I think the Hénon transformation, so this one, in this system, you can see more clearly the fractal structure, and also the logistic function. So basically, it's a function that is used for, the population to describe their evolution. And when you change the first constant, because the logistic function is the function that like you take x and you have 4x times 1 minus x. And when you, 4, it can be a constant, and when you change the constant, the constant in the beginning, then you have one attractor or two attractors, or you can have also like no attractor, because basically you have like an infinite numbers of attractors, and so this is a chaotic system.
Right. Okay. So the idea being that these fractals is sort of like a visual manifestation of some of these properties which are specific to these nonlinear systems. And as you said, a fractal is something that is sort of repeats ad infinitum, independent of scale. So something that you can zoom into, and when you zoom into it, you see a reproduction of its outside structure. So you can't just look at the structure and have an idea of what scale we're looking at. Just as a final note on this idea of fractal structure, because we don't want to focus too much on that, do you have in mind any ideas of like examples of fractals that maybe we see in daily life, or that could be easier to visualize for somebody who's not a physicist?
Maybe, but I'm not sure. But I think sometimes, for example, so I don't know if it's easy to visualize, but I forgot the word.
It's okay. Say it in French.
How do you say it? Poumon?
The lungs.
Yeah,
like
sorry, I don't know if it's very obvious, but when you have, in your lungs, you have a lot of little
like branchings,
branches, towards, in which the air can go through.
Right.
And so these branches, sometimes they, I don't know if it's a really good example, I'm not sure, but
it's a sort of example. They
repeat it themselves, but at a smaller scale each time. And you also have like other examples. But
I guess without going into details, we can sort of measure how much of a fractal something is by what we call a fractal dimension. So it's like 2.5, 2.6 dimensions. So I guess the lungs has a sort of fractal structure, but it's very limited. Another example of something you can think of is like a coastline, right? A coastline. If you look at the coastline of like, I don't know, Norway or France from a satellite, it has a certain shape, and you start zooming in, and the more you're zooming in, the more it looks like it is detailed, and you can keep zooming in until even like the level of the rocks and stuff, and it sort of has this structure that is reproducing. Otherwise, I guess we have mathematical objects which are fractals, like snowflakes. What we call the Koch snowflake is a fractal. The Sierpinski triangle. There's lots of stuff like this. Okay.
Yes. Awesome.
So maybe you talked about controlling chaos. What do you mean by controlling chaos?
So sometimes a chaotic system, it's very hard to predict its behavior. Sometimes we want to control it, and so to control a chaotic system, we can. The goal, for example, is to make the point that represent the system in phase space to stay on only one orbit. So which would make the system a periodic one, and thus a predictable one. And so in order to do that, because usually a chaotic system, the path of the point follow a lot of orbits. So in fact, an infinite number of orbits, but it jumps between orbits each time. And so that's why it's unpredictable, because it's never the same. It never repeats itself, but sometimes the two states that can be really close. And so we try to make the system stay on one orbit. And so this is very hard to do, because we have to change the equations, and it's hard to know which part of the equations to change. So the equations that rules the system evolution. But we can actually do it with AI. I think it can be really useful for this. It also has a lot of application, because, for example, when we study, for example, nuclear fusion, so we are using a tokamak, and which is a very it has the shape of a torus, and so this is used to create plasma. So
for
plasma is a state
nuclear
of matter.
fusion.
Yeah. So also to nuclear fusion. And so plasma is a state of matter where the nucleus are detached from the electrons, and so it can has a chaotic behavior, And to kind of control this plasma, we can use AI, and it has been able to detect, I think, 80% of the impending instabilities, so it can be really useful to control the chaos.
Are there any particular applications where we're actually putting this into work and doing something with it that you can think of?
I think also the fact that some robots are able to walk. So, I think there are companies that are creating robots that are able to walk, to do different tasks. And actually, if we weren't able to control the chaos, then they wouldn't be able to walk, because it can have the robots can be a kind of like chaotic system, and so by controlling it, we can,
So I guess this is what we're talking about, like the electrical signals, all the information coming in from their sensors that they have to be digested and then sort of used to make decisions and control movements, and just I guess kind of like the way the human
yes, because
motor
also
system
the
works.
human body, there are a lot of chaotic systems. So like, for example, the breathing patterns, the heart rhythms, like the neural signals between
Right, so I guess chaos is sort of all around us, but chaos in the physics term, not in the popular sense of the word. Okay. I guess we also have a lot of chaos and nonlinear behavior in fluids.
Yes, with fluid turbulence.
Right.
So maybe I can talk about that a little bit.
Sure, we'll quickly go over that, and then we'll get to Jeanne's part, where she's talking about a lot of the applications we have in biology, economics, and all these things.
So turbulence, it's usually a classic example of a chaotic system, so in fluid physics, because it illustrates kind of like how a smooth, so what we call a laminar flow, can transition into a turbulent one, since, for example, like the temperature can increase.
Mm-hmm.
So usually if you have a fluid that is heated from below, it forms kind of like convection rolls. But if you turn the heat higher, then these rolls become unstable and they start to wobble.
Yes.
And eventually they can turn into unpredictable and chaotic flows. So this turbulence arises from nonlinear internal interaction in the fluid, making it extremely sensitive to initial conditions. And so small changes in speed or pressure can alter like future behavior. And because of this unpredictability, scientists use often statistical models to describe general properties of turbulent flows, such as energy dissipation and vortex formation.
Because the actual finding analytical solutions to those equations is very, very complex and very, very
usually
difficult to do, which is why, especially now that we have very, very powerful computers, using statistical approaches, modeling is much, much, much more useful. And I guess there's applications of that everywhere, from like aerodynamics for cars and planes to meteorology to air patterns, wind patterns, and all that. Okay. Maybe we can open up the floor a bit more to Jeanne, who can talk to us a little bit about some of the other applications that I think that was what you mostly focused on during your presentation, if I'm not mistaken. So let's get to that then. Maybe I'll let you go in whatever order you find most interesting.
So, chaos theory has wide applications in many subjects, so in our daily life with biology and economics, but also in meteorology and physics, as Carla said. So, for instance, in biology, it can explain the unpredictable population dynamics. A great example is the dynamic between lynxes and hares, because they don't follow regular cycles. They shift seemingly erratic ways due to changes in reproduction or maybe food availability. So there are also applications in biological rhythm because of irregularities in heartbeats, for instance, so they can be modeled using chaotic systems, and that said, it helps the doctors to detect conditions like, for instance, atrial fibrillation. So Carla also talked about meteorology because chaos theory underlies the butterfly effect, where something as small as a butterfly flapping its wings could theoretically influence a storm.
Right.
So
and traditionally, I guess chaos theory comes from the study of atmospheric systems. So I think that is where there's a lot of really interesting applications of it, right?
Yeah, exactly. Because in weather, it is mostly impossible to predict the weather over 1 week because of the sensitivity to initial conditions. Beyond that, a tiny input error grow exponentially.
Right.
And I think a very important application of chaos theory is also in economics, because it has transformed how we view markets and financial systems. For example, a traditional model assumes that economies naturally tend toward equilibrium, but with chaos, we have shown that small, harmless action can trigger large-scale disruptions. For example, the 2008 financial crisis, which began with a default on subprime mortgages. It's a relatively small segment of the market. It quickly spiraled into a global meltdown in the world due to interconnected financial instruments. Similarly, the stock market can behave chaotically because a single news story or earning report might trigger a cascade of trades due to sometimes algorithmic reactions or maybe investor sentiments. In economics, the market theory doesn't tend toward equilibrium because of many aspects, from actions on the market to feelings from the investors.
So I guess just to make the comparison, so when you're talking about economics or other system, what these different things that you're talking about are the different parameters that would go into some sort of an equation. And the behavior of that equation. Right.
Yeah.
Go ahead.
If we change these parameters, there are lots of change after in the output.
Right.
So because this is a nonlinear system.
Right. It's a nonlinear system, and then so we hope that the way that the equations that model this, the chaos that comes out of that looks like and is comparable to the chaos that comes out of what we actually observe in the real markets and real financial systems. Right.
Because in school,
Yeah, go ahead.
In school, we always teach that in market there is one equilibrium, but we have seen many times with crisis in the world that it's not true.
Okay, I maybe we can go more into that because you, if I'm not mistaken, this year you're specializing and majoring in economics. So maybe you can talk to us a little bit about that. So because I'm not particularly well versed in it, I don't think Carla is either. So. Do you want to maybe just talk very briefly about that, what you mean by these ideas of equilibriums in the markets and how maybe this ideas coming from chaos theory help us better model all that?
Yeah, sure. In economics, equilibrium always refers to a state where there is equal demand and offer with no external pressure pushing the system to change. However, with the chaos theory, it challenges this assumption because the economical system is dynamic and non-linear because it involves countless of agents that are interacting together and that are making decisions that can impact the whole system.
Yeah.
These systems actually can evolve far from equilibrium because of sometimes policy decisions or confidence ones. We have seen this with crises like the flash crashes where markets plunge within minutes before recovering. And so, yeah, this chaos theory application in economics is particularly true during financial crisis,
Right.
with speculative bubbles or market crashes, where feedback loops can push the economy further away from the balance.
Right. I think this is very key, what you're talking about, feedback loops, because this is at least something I'm more familiar with, and you talked about in biological systems. Usually, between the time, for example, a sensor captures something, and then there's a time between an action is taken, there's a feedback on that thing with a time delay, and those time delays are what usually bring in the non-linearity into a system. And I guess in economics, for example, with stock market trading, the feedbacks and the delays between the time the feedback is like sort of arrives between the time the decision is made and the time the effect is seen is what creates this non-linearity in the system, if I'm not mistaken.
Yeah, the fact that feedback loop is a process where the output is not proportional to the input, and so in economics, as I said, a simple change in the input, process to a completely different output. Yeah.
Okay. And so, how far have we gotten in using chaos theory to do a proper sort of modeling of these sort of phenomena? Have we gotten far with it? Is it something that is actually used currently? Is it very conceptual, or is it actually something that is done?
Well, as we know that these systems are very
Non-linear, I guess, very sensitive.
Sensitive and applied to chaos theory. We have put in place algorithmic traders or chaos-based models.
Yeah.
Sometimes to detect early signs of instability, so we can find solutions more faster. And I also know that central banks use chaos to better anticipate the effect of policies, like, for example, the interest rate adjustments.
Mm-hmm.
So the chaos theory gives the economists a more realistic lens through which to understand and to prepare for volatility in complex financial systems. However, it is still very hard to predict anything more than 1 or 2 weeks.
Mm-hmm. Okay. So it's still a very, very complex, very highly non-linear sort of system, even more so than a lot of these physical systems like the atmosphere.
Yes, indeed.
Okay. So that's very interesting. Maybe we can start moving towards the end, because we've already used up most of our time. You also talked about, just in general, before going into this, you talked about deterministic systems in general, and just the idea of dynamic systems. Maybe we can sort of finish up on that.
Me?
Yeah.
Okay. So a dynamic system is basically a system that evolves over time according to many rules or laws. So the key feature is that the system state changes often continuously as the time progresses. So we can take the example, the motion of planets, of population growth, or, as Carla said, swinging pendulum. And a deterministic system, on the other hand, is one system where the current state completely determines the future state. So there is no randomness involved.
Right.
And what is interesting is that all deterministic systems are dynamic, because if they evolve over time, they are dynamic if they evolve over time. But not all dynamic systems are deterministic.
Okay.
I would say that the main difference lies in the role of predictability and randomness.
So I think the interesting thing is, because you guys are also talking about determinism this year in your senior year in philosophy class. So the idea of deterministic systems is that each step determines how the next step goes, and it follows like a ineluctable rule, right? So like when we talk about Newtonian mechanics, it's a deterministic system because every instant determines what happens in the next state. And so we might have the tendency to think that a deterministic system is a system which is perfectly predictable. That's where chaos theory comes in. It says that you can have a system that is perfectly deterministic, but still difficult to predict because of this key point being that nonlinear dynamic systems, nonlinear deterministic systems, are systems where even the smallest changes in the initial conditions create big changes in the end, which makes the system unpredictable, which is kind of interesting because we have opposing that something like, for example, quantum mechanics, which is fundamentally non-deterministic, which is fundamentally probabilistic. Okay. I think we've gone through most of the topics that you guys brought up. Is there anything that you want to talk about that we didn't really go over?
Maybe,
Carla?
I'm not sure, but there are like three main forms of emerging chaos. So like ways for chaos to emerge into a system.
Mhm.
So I don't know if it's really interesting.
Maybe you
but
can
we
give us a very quick idea of what you mean by that.
Yes. So for example, there are systems that are periodic at first, and if we change one parameter, it starts doubling its period. So going from 1 cycle to 2 to 4 to 8 and so on. And so at some point it becomes chaotic. Then there is quasi-periodicity. So it's a bit more complex, but it occurs when a system exhibits motions that involves 2 or more independent oscillations or frequencies that never exactly repeats over time because the ratio is irrational. So it's a bit complex, as I said,
Right.
but think of it as a mix between order and complexity.
Okay.
So it's not quite repeating, but it's still not fully chaotic. So for example, we can imagine a point that is moving around a circle at one speed and up and down along a line at another speed. If the ratio of these two speeds is irrational, then the path it traces will never exactly repeat, and it will fill out a kind of torus, so like a donut-shaped surface. And then the third form of emerging chaos is intermittency. So it's when a system seems to behave regularly, but then it suddenly and unpredictably switches into a chaotic phase for a short time before returning to a regular behavior.
Okay. So there's even sort of classification and structure within chaos, and it's not just chaos, different types of chaos, different ways of measuring this, right? That's what we like to do in general in physical sciences, be able to measure and classify things. Okay. I think we've gone over most of the stuff that you talked about and even gone into maybe even further detail for some of them. It's not an easy topic to talk about without visualization, I think. So you guys, I think, have done a pretty good job of talking about it on the radio. But so as usual, I think I'm going to ask you the same question I ask of most our guests. What was your experience doing the research for this? What was your experience that you found very interesting about this, which was very surprising, striking? Maybe we can start with Jeanne.
Yeah, sure. So I think that this subject is very interesting because we usually don't know that weather or even heartbeats are controlled by or in a dynamic and non-linear system. And I also think that Carla talked about this, but the three body problem was a very interesting part of the subject. And it shows really how complex our universe is, and that we can't always determine. I think it's very interesting because in physics we always learn many formulas and everything, but actually it's much more complex than all this.
Well, the physics we do in high school, at least, is very basic compared to what real physics is next. Once you start getting into it, and I think the limit, as you've seen yourself, is the mathematical side of it. And also, I think one thing that became clear with chaos theory is that what really opened the door to studying this, it was our capacity to actually use computers to do modeling and then see all these different behaviors as opposed to doing calculations by hand. Okay, and Carla, what was your experience like with this topic?
So I didn't really knew what was chaos theory before, but I think it's really interesting, And also, what I thought was very very interesting is that it's not only in like physics STEM, it's also like in biological being.
Yeah.
And so, for example, I thought it was very interesting to find out that our heart rhythms, our also neural firing and the breath patterns, they are chaotic system, and I mean it's crazy to think like, for example, epilepsy is due to a chaotic brain waves activity. So
if anything, I think what is interesting, because I did a bit of my studies on these sort of modeling of these chaotic systems, specifically to the heart, but also it's as valid as anything else with the neural networks and the neural firings, as you said, is that the signs of good health are actually chaotic behavior. And when things become regular and periodic is when the system is actually not functioning properly. Yes. Whether it's talking about the case of epilepsy, where we were during seizures, the neural firing patterns become very regular, and same with heartbeats. So it's kind of counterintuitive. But I think one of the things we didn't talk about is that systems which do behave chaotically also have much more adaptability, whereas periodic systems are much less adaptable to perturbations to the system. But who knows?
Because
maybe.
Also, I think.
Yeah. Go ahead.
Also, I think for example, if your breathing patterns become too regular, I think that you can have like sleep apnea, so which is not great also. And but not too good, because for example, if you have if it's too chaotic, then you can have some illness. So for example, like ventricular fibrillation, I think. So which can be very dangerous, and it's when your heart beats too irregularly. So that's not good either. But it's very interesting to know how chaos can emerge into, for example, so the heart rhythm. And so it's when the true part of the heart beats, but not at the same speed. And I think so. That's very interesting.
It's for sure that I think one of the things that we've discovered with the, discovery of chaos theory in the 1960s and its development through the 70s, 80s, and so on, is that it is almost like a new sort of mechanics, right? So we have quantum mechanics, we have classical mechanics, and then sort of we have chaotic mechanics, or nonlinear dynamics, as we call it more precisely, which is a new way of looking at any sort of a system that evolves, which is complex. And that pretty much is most systems, which are real systems, whether it's financial markets, whether it's biological systems, or it is behaviors of systems of particles. Right? So it's like almost a new language for studying complex interactions, even if they are deterministic in their physical nature. Okay. Well, thank you, Jeanne, and thank you, Carla. Your topic was very, very interesting, very close and dear to my own heart. And I think you guys did a really, really good job of making it easy to understand while giving an idea of the extent of this sort of mechanics. So thank you very much. And I hope that you guys enjoyed it as much as we did. So that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.